Hello everyone, welcome to video number 2. Thank you for joining me. I would like to discover a different formula now, which has to do not with the interior angles, but has to do with the number of total diagonals in each figure. So again, just like the last discovery, I'm going to draw just a basic 3-sided figure or triangle, 4-sided figure, 5-sided figure, 1, 2, 3, 4, 5, and 6-sided. 1, 2, 3, 4, 5, 6. And so this starts off in a very similar way to the last one. The number of diagonals you can draw from one vertex. So in the last example here, we could not draw any more diagonals. So there's 0 diagonals from each vertex because everything's already drawn. In a 4-sided figure, if you drew a vertex, you could only draw one other diagonal because the other 2 are drawn. If I picked this vertex in a 5-sided figure, you're able to draw 2 more diagonals. And in a 6-sided figure, if I picked this vertex, you're able to draw 1, 2, 3 diagonals because everything else is already drawn. And so this is going to be important later when we actually discover the formula. But if I took it a step further, and in red here, if I tried to find the total diagonals in a figure based on just what I have. In a triangle, if I looked at any of the other vertices, I can't draw any other vertexes. So the total diagonals in a triangle would be 0. In a square, I could also draw this diagonal, but I think that's the only other one. So there'd be 2 total diagonals in a square. In a 5-sided figure, I believe I could draw a diagonal here and here. And I also could draw a diagonal here, makes a nice little star. And I think that is the total number of diagonals because remember, the diagonal from this vertex to this vertex is the same diagonal as if you go from here to here. So there's really only 5 lines. So there's 5 diagonals in a 5-sided figure. And in a 6-sided figure, I have 3 already drawn. But if I decide to go from this vertex, this one already exists, but I can draw a diagonal here and here. This diagonal, this one already exists, but I can draw one here and here. And this vertex, this one exists, this does not exist yet, this exists. And then I think in black, this one, we have one here, here, we can draw one here. So, and then this vertex, I think we have 1, 2, 3, 4, 5, 6, 7, 8, 9. I see 9 diagonals total in a 6-sided figure. So again, if you picture it like the last time, and I ask you to keep going to a, again, 100-sided figure, you would look at me and say, what are you, crazy, Mrs. Logus? I don't want to draw a 100-sided figure and then try to draw all the diagonals because a 6-sided figure already is crazy enough with 9 diagonals. You're nuts. So instead of asking you to do that, what if we found another interesting formula like the sum of the interior angles one? So I notice again, when we're going from the number of sides to the number of diagonals drawn from one vertex, it looks like we're consistently subtracting 3, again, from n, the number of sides. So I'm going to write myself a note that it looks like we're consistently taking the number of sides minus 3. And something else I notice is that we somehow need to get from here to these final answers. So we need a formula where we get these as our final answers without drawing the picture ourselves. So I start to notice something. If I take 3 times 0 and then divide that by maybe 2, I get 0. If I take 4 times 1 and divide that by 2, I get 2. If I take 5 times 2, 10, and divide that by 2, I get 5. And if I take 6 times 3, 18, divide that by 2, I get 9. So each time I'm taking this number times this number. This number is represented by the number of sides, n. These blue numbers are represented by the number of diagonals, which we represented already as the sides minus 3. And then to get to these final numbers, I divided everything by 2. So I'm thinking based on the numbers that I see, that if I take the number of sides multiplied by the sides minus the number of original diagonals, I can get my answer. Let me again check to see if this works. Let me check, because I did this last time, let me check where you have n equals 6 sides. So if this is what I had instead, and I plugged 6 in for n, 6 times 6 minus 3 over 2, I would get 6 times 3 over 2, which is 18 over 2, or 9 diagonals. So again, just like the previous one, if I wanted to find the total number of diagonals, I would take n 100 times 100 minus 3 all over 2. And if I calculated that, that would get me my total number of diagonals without drawing a picture at all. So in summary, the number of diagonals that can be drawn is the number of sides times n minus 3 all over 2. So keep that one in mind as well. So because we discovered the sum of the measures of the interior angles, I think it's only right if we discover the sum of the exterior angles of any polygon as well. And just to make our lives a little easier, let's assume that all of these figures are equilateral, aka equiangular as well. So this triangle is really equilateral. This shape, if all sides are congruent, is probably really a square. All of these sides are congruent as well, and so forth. So let's go with what we know. From the past, we know that an equilateral triangle has all interior angles being 60 degrees. And we also know that each vertex really does have an exterior angle, and these two are supplements. So this angle here would be 120 degrees. If this was extended, this would be 120, and also this one would be 120. So if I were to find the sum of all the exterior angles, and I added up 120, 120, and 120, I get 360 total degrees. What if we looked at a square? We know that the interior angles of a square are all 90. So if we extended every single vertex, the exterior angles here would also all be 90 because they're supplementary to the interior angle. So if we added 90, 90, 90, and 90, we would also get 360 degrees. Interesting so far. Let's keep going again. We haven't studied pentagons as much, but we know from earlier that the total interior degrees is n minus 2 times 180. Because there are 5 sides, this is really 3 times 180, or 540 total interior degrees. Because this shape is equilateral, that means that all these angles are also congruent because it would lead to equiangular. So if we took 540 and divided by 5, we would get that each interior angle is 108 degrees, which means every exterior angle would be the supplement of 108, or 72 degrees. So again, I can go around and extend all of these. If I did extend all of them, each exterior angle would be 72. So if I did 72 times 5, interestingly enough, I would also get 360 degrees for the sum of the exterior. This is getting too weird not to be a pattern. Let's check out the hexagon as well to see if this works. All sides are equal, which means all angles are equal. If you did n minus 2 times 180, or 6 minus 2 times 180, 4 times 180, gets you 720 total degrees. If you divided that by 6, each interior angle all the way around would be 120 degrees, which means that each exterior angle, no matter where you extended it, every vertex would have an exterior angle of 60 degrees. If I took every exterior angle, 60 times 6, look at that. Yet again, there's 360 total degrees. So guess what? That 100-sided figure we've been talking about, if you didn't even want to draw a picture, that 100-sided figure, no matter what, would have 360 total exterior degrees. So if one exterior angle is taken at each vertex, the sum of the measures of the exterior angles in a polygon is always 360 degrees. So let's use some of these things to start applying to some problems. For instance, here is a random 4-sided figure. So as soon as I see a 4-sided figure, notice that we're dealing with interior angles. So I'm thinking n minus 2 times 180 might come in handy. There are 4 sides, so n is 4. So if I take 4 minus 2 times 180, or 2 times 180, there are 360 total degrees in this figure, which means that x plus 8x plus 7x plus 2x wouldn't equal 180, it would equal 360. And so if I continued to solve that problem, we would have, let's see, 18x equals 360. If I take 360 divided by 18, I would get x equals 20. And it wants to know the measure of angle G. Well, I didn't label that. Let's say for the sake of argument that this is the measure, this angle is called G. So that means that this angle would be 160 degrees. Second example, using a dodecagon. You might remember from earlier, a dodecagon is a 12-sided figure, which means that n equals 12. Find the sum of the measures of the angles. Now, your book tends to say this type of language, so I want to clarify it. When it says find the sum of the measures of the angles, please assume that the book is talking about interior angles, not exterior. So if you want to find the measure of the interior angles, that is, again, n minus 2 times 180, or the number of triangles. Because n is 12, you really have 12 times minus 2 times 180, or 10 times 180, which would get you a total of 1,080 degrees in your figure. Find the sum of the measures of the exterior angles. I don't need to do any work for this. The sum of the measure of the exterior angles is always 360, no matter what. Find the total number of diagonals. Well, that other formula that we discovered earlier was the number of sides times the sides minus 3 over 2. Because the sides, again, are 12, it's really 12 times 12 minus 3 over 2, or 12 times 9 over 2, which would get you 54 diagonals. This next example looks a little bit more confusing than it really is. It looks like we have 1, 2, 3, 4, 5, 6 sides, so it's a hexagon, which really means that the number of sides, or n, is 6. So if my goal is to find the measure of angle A, I know that all of the interior angles here would have to add up to a particular value. And to find that particular value, you would do n minus 2 times 180 to find the total degrees, as we've been doing. So n is 6. So this is really 4 times 180 degrees, which is 720 total degrees. So if we made up a little equation here, we could say that all of these angles added up equals 720. So if I did that, I would get that, let's see, if I add these up, we have 4x, 5x, that's 9, 10, 11, 12, 13, 14. So we have 14 x's plus, if we add 10, 110, negative 2, 20, and 140, that would be 278. So all of this added up would equal 720 degrees, which means 14x, if you subtract this over, would be 442. X would be a little unfortunate. You would get 31.57, which is correct. But if you wanted to find the measure of angle A, you just have to plug the 31.52 in for X. And if you did so, you would get a value of 155.85 degrees. One more example before the next video. What is the name of the polygon if the sum of the measures of the angles is this? So now we have to work backwards, because if we need the name of the polygon, we need to know the number of sides. So this time, we know that the interior measurement is 1,080. So we're going to work backwards. If we solve this equation for n, rather than distributing, I would suggest dividing both sides by 180. And if you did so, you would get n minus 2 equals 6. And then if you added 2 to both sides, you would get n equals 8. So the actual answer, the name of your figure, would be an octagon. All right, guys, so please tune in for the next video for more examples.